Years ago, I was the lead security software reviewer at ZDNet and then at CNET. And I remember testing an internet suite from a major vendor, and I won't say which one, and it included a password manager. You know, the feature that retains various passwords that you have for your websites and also generates new passwords that are sufficiently long and secure and otherwise you wouldn't be able to remember on your own. Anyway, I was testing this suite when I happened to randomly strike two keys. I think it was Control and B, and up popped the password manager displaying all my test passwords in the clear. The thing was, the manager required its own password, which I had not entered. Remember, I only hit two keys, and I was able to repeat the process over and over. Clearly, this was a software flaw. So I reported this flaw to the vendor, and the response was not what I expected. "Why did you press those keys?" "Doesn't matter," I replied. "You still have a bug." And they said, "Not if you don't strike those keys." Well, several days passed and the product shipped, and in my review, I said something to the effect of, "Be careful with the password manager, it's got a bug." Of course, the security company freaked out, they called the editor-in-chief, they threatened to pull their advertising. But really, shouldn't they have just fixed the password manager when they could? My example of hitting random keys and forcing a password manager to pop open illustrates the topic of this episode. Fuzz testing is similar to randomly striking keys and producing unexpected results from the software. Except fuzzers automate the process and can iterate through thousands of test cases in a matter of minutes. And modern fuzzers are not random, they're guided, so they dynamically work through the code, increasing their code coverage to find unknown vulnerabilities that can escape other software testing, such as static analysis. In a moment, I'll tell you about a flaw discovered only through fuzz testing in a very old open source product. It's a flaw that hid itself for more than 20 years and remains perhaps the most dangerous vulnerability ever discovered. Welcome to The Hacker Mind, an original podcast from For All Secure. It's about challenging our expectations about the people who hack for a living. I'm Robert Famosi, and in this episode, I'm going to talk about how fuzzing has evolved over the years, how open source projects have, for the most part, gone untested over that time, and how new efforts to match fuzzing to open source are today helping discover dangerous new vulnerabilities, such as Shellshock.
And we thought Heartbleed was bad. Welcome to Shellshock, the latest security threat to hit the internet, and it's a doozy.
In the fall of 2014, Shellshock was publicly disclosed. It's a fundamental vulnerability in Bash, which is a command shell used in many computers, including Macs. And as this Mashable reporter commented, if exploited, Shellshock makes it ridiculously easy to execute malicious code.
So here's how this vulnerability works. Bash lets users define functions as a way to pass text onto other systems and processes. Usually this is just fine, and hey, it's convenient. This is what it's for. The problem is that this vulnerability, which includes specific characters as part of a definition, occur because Bash doesn't stop processing a function after it's defined. It'll continue to read and execute shell commands following the function definition. The end result is that basically the malicious attacker can get shell. And if you are a malicious intruder, that's what you want. You want to get access to the command line on a server, because that means that you can then execute all kinds of malicious code. You have access to system files. You can share what you're finding with the system on the world. We want to be clear, getting shell is not the same as getting root, but it does mean that intruders have a chance at an extra special bonus round known as privilege escalation.
It's like the operating system left the front door wide open. How did this happen? Our story begins in the 1980s, where both the tool used for this discovery and the Bash shell were first created. In the fall of 1988, Professor Barton Miller was teaching his graduate Advanced Operating Systems class at the University of Wisconsin, Madison. One of the class projects was to fuzz test Unix applications with a new technique, fuzzing. Barton had created this technique after noticing during a summer's thunderstorm that the ambient electrical impulses during a remote login session had changed his inputs and therefore his results. And he began to wonder if sending unexpected inputs would trigger unexpected results. He wrote his program, which he simply called Fuzz, saying it generates a stream of random characters to be consumed by a target program. In a subsequent academic paper, Miller demonstrated that 25 to 33% of the Unix applications tested with Fuzz either crashed or hung when reading random input. After testing Unix, Miller went on to test Windows NT and other systems. What's nice is that the Fuzz program recorded what input had been sent, and that record allowed other researchers to later reproduce the crashes and therefore isolate the vulnerabilities. One of those vulnerabilities was the gets finger vulnerability. The name comes from the finger protocol, which provides status reports on a particular computer system or a particular person on a network site. For instance, I can use the finger protocol today on my Android to see what other devices are on a shared public Wi-Fi. Back then, finger was perhaps useful to see who else was on the network at that time, so you're able to chat with them over Telnet or meet them in person. The name literally comes from the idea that one could run a finger down a directory of names to find someone they were looking for. What's interesting is that in November 1988, Robert Morris Jr. used vulnerabilities in SendMail and the FingerD protocol to construct, unintentionally, what would later become the first internet worm. What's a worm? Computer viruses, for example, have to spread via humans, via email attachments. Worms, by comparison, are able to replicate on their own, so the Morris worm exploited an overflow vulnerability in Finger to spread from system to system. And once a successful worm had been demonstrated, internet worms became more common in the early 2000s with Code Red, Blaster, and others. In 1995, Miller co-authored 4 papers arguing that the reliability of software was getting worse. He cryptically wrote that his fuzzing activity, in addition to helping to find Get's finger vulnerability, had found other software bugs that might indicate future security holes in a variety of different systems. Unfortunately, his warning went unheeded at the time. That's the tool side. There's another side to our story, the target, and it also begins in the 1980s. Up until the 1970s, there were only a few operating systems, in part because computing was still a large enterprise operation requiring massive machines. Only large enterprises such as AT&T had the computing power and the developers to create their own applications. In the 1970s, the Bell System Labs, owned by AT&T, set about creating the Unix operating system for its own internal use. By the late 1970s, however, AT&T began to license Unix to outside parties and universities. This prompted a number of variants, such as the Berkeley System Distribution or BSD Unix, Sun Microsystems Sun OS, and even Microsoft had its own flavor called Xenix. AT&T later sold Unix to Novell, who in turn sold it to Santa Cruz Operations or SCO Unix. But I digress. It also prompted a movement toward license-free software, and in September 1983, something called the Free Software Foundation was announced at MIT. One of its early goals was to gradually rebuild all the components of the Unix operating system and share it with the world for free. This was the beginning of open source software. These free software components carried the name GNU, spelled GNU, which stands for GNU is not Unix. Okay, that's some OG hacker humor, if ever. I'm sure a few people are going to tell me that it's pronounced new with no G, but people who used it extensively back in the day have assured me it is pronounced GNU, so that's what I'm going to use. One of the most important features of any operating system is its shell. What is a shell? A shell is simply an interface for the operating system. It's where you run commands, programs, and scripts. For simplification, you can think of it simply as a command line. Bash, then, is GNU Project's shell. Remember, GNU is not Unix. In keeping with that humor, developer Brian Fox wrote his own shell, and he called it Born Again Shell, or simply Bash. Bourne in this case is not Jason Bourne, the spy, but Stephen Bourne, who at Bell Labs wrote the original Bourne shell for Unix. Remember, back then in the 1980s and early 1990s, the internet wasn't as fully operational as it is today. So there's this crazy story about Fox driving cross-country with a carload of computer tapes containing his original version of Bash. He was driving from MIT to California to share his program. And that's a good thing that he did. Bash rapidly grew in popularity in part because it was used as sort of a glue that held pieces of the early internet together. And why not? The Bash shell Fox created was simple yet powerful. Want your web server to get information from another computer's files? Make it pop up a Bash shell and run a series of commands. Today, Bash remains still an important part of the toolkit that helps power the web. It's on your Mac and virtually any computer that runs the Linux operating system. And while it's not on Windows, it can be added. Sometime in late September 1989, and we don't all agree on the exact date, a serious vulnerability was introduced into Bash. And it may have been introduced by Fox, or it may have been introduced by Chet Ramey, who was an intern at the time and later took over maintenance of Bash. It doesn't matter who introduced the flaw. What does matter is that the flaw in Bash would sit unnoticed for the next 25 years. There's a saying within the open source community, given enough eyeballs, all bugs are shallow. It's called Linus's Law after Linus Torvald, who created the Linux operating system. But it's actually from Eric S. Raymond, from his 1999 book, The Cathedral and the Bazaar. Anyway, the idea is simply this, that unlike proprietary software, where the source code is hidden inside the company's domain and therefore not available to be audited by outside sources, open source code is available for anyone to audit. The fact is, over 85% of the software today is composed of third-party elements. And a majority of that third-party software is often open source software. And that only makes sense. Why should I attempt to create my own SSL TLS when I can integrate OpenSSL into my product? Not only do I get much faster time to market, I don't have to worry about rolling my own encryption. Really, never roll your own encryption. Just don't. But eyeballs aren't necessarily on all the open source code that's out there. And what may have been seen as secure in the 1980s and the 1990s certainly would not be seen as secure today. Take IoT, where we find ourselves using MMQT and other ancient protocols, not for what they were originally designed for, but for our immediate need for lightweight communications among devices. But I digress. So, after 1995, when Miller published his papers, there didn't seem to be a lot of testing going on. That's not to say there was no testing, because there was. It just was very hit and miss. And part of that was that Miller's fuzz application remained largely in academia and not well understood outside of that. Our story now skips ahead 20 years to the year 2014. In April of 2014, the Heartbleed vulnerability was disclosed by Codenomicon and Google researchers who independently found it using fuzz testing. In a previous episode, episode 10, I talked about Heartbleed. While it's not necessary for this episode, I will be referencing Heartbleed, so if you want to learn more about it, check out that episode. Basically, Heartbleed was a vulnerability in the heartbeat function of OpenSSL that existed for over 2 years before it was found. This was a serious vulnerability, one that would leak passwords and encryption keys over the internet. And it simply would not have been detected using traditional static code analysis tools. No, for this new class of vulnerability, you needed to test it dynamically while running the code. You needed fuzz testing. There are, of course, different types of fuzzers: random, generational, protocol, guided. We're not going to get into them here, or the fact that Heartbleed was discovered mainly because the protocol fuzzing tool only looked at the specs for SSL protocol at the time. And one could argue this gave them a huge head start. For this episode, really we only need to talk about one fuzzer, American Fuzzy Lop, or as it's commonly known, AFL. A fuzzy lop, by the way, is a type of rabbit, which is why you see the image associated with AFL. AFL was created by Michal Zalewski, and it required you to recompile the application with a special compiler wrapper that adds assembly instrumentation code to the binary. So it doesn't need the source code, only an input. Further, it starts with an input sample or seed that triggers a new code path and uses that sample as a starting point for further fuzzing. What this does is allow for even more code coverage than, say, a random fuzzer. And having that extra depth will be very important when it comes to Shellshock. Zalewski made AFL openly available under a free license. As free fuzzers go, AFL is pretty easy to use, but to use it well, you more or less have to study it or find an expert who already has. So you have a fuzzer, now what do you want to fuzz? In the summer of 2014, the Linux Foundation rounded up $6 million in a war chest and announced that it would shore up the security on a few widely used open source projects, such as OpenSSL, which is where Heartbleed lived, OpenSSH, and the Network Time Protocol. Bash wasn't on the list. So if Bash wasn't on the list, then how did we end up with Shellshock? The discovery of Shellshock perhaps really begins with a researcher questioning some unusual behavior he experienced. Stefan Shesla told Stack Exchange that in July 2014, he'd experienced a vulnerability in glibc localization. It was a multiple directory transversal vulnerability within the GNU C library that allows attackers to hack into Git servers provided they were able to upload files there. This was CVE 2014-0475, which stands for the year of its discovery, 2014, and the number of the vulnerability reported, in this case, 0475. CVE 2014-0475 was not Shellshock, but in this case, Bash was used as the login shell of the Git user. And this early work with Bash probably got Shesla thinking about other things that led him to Shellshock. What he noticed as he continued to fuzz was that Bash seemed to allow an adversary to run malicious code unchecked on another system because Bash was not properly sanitizing its input. Well, what does that mean, sanitizing? Sanitizing generally means that the application looks for invalid inputs and rejects those that don't conform to its specifications. What he noticed was that he could add some details to a Bash request, and Bash would go ahead and simply process the request without question. He noticed this when using OpenSSH. SSH, or Secure Shell, is an encrypted connection over port 22. It is used to connect two computer systems together securely, and the connection is encrypted, so you can type on one and see the result on another. And this is where we start, with OpenSSH. Shesla reported the initial Shellshock vulnerability, CVE 2014-6271, on September 12, 2014, but it was not made public then. Whenever a vulnerability is discovered, it is the responsibility of the discoverer to first inform the vendor, or in this case, the open source managers, privately. This is not a rule, but it's really good software etiquette. Over at Bash, Brian Fox had since moved on, so Shesla reached out to Chet Ramey, who, on September 16th, began creating the fixes for the current and past versions of Bash going all the way back to version 3. Concurrently, Florian Weimar, who works at Red Hat, confirmed Shesla's findings and helped him get in contact with other relevant parties in secret with a few select internet infrastructure providers and Linux distributors, including Debian, Red Hat, Ubuntu, SUSE, and others. Delays in publicly reporting vulnerabilities like this is sometimes necessary and has happened before, but only when the vulnerability is particularly significant. For example, through the use of both the Finnish and US CERT, the details of Heartbleed were given to several companies ahead of public disclosure, making sure that banking and e-commerce sites that used OpenSSL were patched in time. Perhaps a more significant example was back in 2008 when researcher Dan Kaminsky found a fundamental flaw in the domain name system protocol, one that could lead to cache poisoning. Before he presented his findings publicly at Black Hat USA, Kaminsky coordinated his discovery first with all the major internet players. And for that simple courtesy, Kaminsky is often cited as the man who saved the internet. It is also possible that Shellshock could have taken another route entirely. Rather than reach out to Weimar, Shellshock could have sold his vulnerability on the dark market, or directly to an intelligence community. He told the Sydney Morning Herald, "We joked about how much I could sell to GCHQ or NSA, or negotiate a pay raise. But in my mind, it's never been in doubt that the first thing to do was to get it fixed ASAP and minimize the impact. My job as an IT manager is to minimize the risk and to put out fires." When Shellshock's initial vulnerability in Bash finally became public on September 24th, he nicknamed it Bashdor. It was immediately a big deal, at least online, as researchers began to see how it could be exploited, how bad it could be. In fact, the MITRE organization gave this CVE a severity rating of 10 out of 10. So our story really could have ended here. I mean, Shellshock responsibly disclosed a 20-something-year-old flaw in Bash, appropriate companies were given a heads up, and a vulnerability was given a CVE with a high severity rating, and a patch was publicly available. All good, right? Unfortunately, CVE 2014-6271, aka Bashdor, was only the tip of the iceberg. As different online forums and listserv groups began to buzz about the Bashdor vulnerability, they quickly settled upon something really important to discuss: its name. Clearly, Bashdor was uninventive, and, well, it didn't have a cute logo. So Bashdor quickly morphed into Bashbug, which did have a cute logo, and that was quickly followed up with Shellshock, a name first accredited to Andreas Lin. And with that came an even better, if subject to possible copyright violations, cute logo. Shellshock as a name then stuck and became the name going forward. This momentary obsession over the name is not entirely a joke. I know there's a whole pro and con argument within the InfoSec community about whether to name critical vulnerabilities, and certainly whether or not they need a cute logo. Okay, maybe we can all agree to forego the cute logos, but I asked the people at Codenomicon who found Heartbleed, and I asked them specifically about the criticism they received in naming that. They argued back, really, no one's going to remember CVE 2014-0160. That's true, given that this episode has talked about CVE 2014-0475 and now CVE 2014-6271. I think you can start to see the confusion here. So when we give the really severe vulnerabilities unique names, they do stand out more from the thousands of other CVEs given in a single year. Not only that, the named ones get the media visibility that is sometimes necessary to get the patch out quickly. Really, would you have listened to a podcast about CVE 2014-6271? In retrospect, this naming conversation was really a good thing because Shellshock didn't end up being just one CVE. There were multiple CVEs, so deciding upon a name early was a good thing, since it did keep things straight when talking to other InfoSec people. But the name wasn't the only controversy lighting up the online forums and listservs. It seems more than one security person had the uneasy feeling that the original Shellshock CVE only scratched the surface. And they were right. The initial understanding of the problem was faulty, so the patch developed did not fully solve the problem. Whenever a patch goes public, both the good guys and the bad guys have access to it. They both reverse engineer it, meaning they try to step through what parts of the code were changed so they can get some idea of what the original vulnerability might have been. So it's a race to see if anyone can exploit that flaw before everyone gets their system patched. That's on the bad side. On the good side, researchers try and reverse engineer so they can look for other vulnerabilities like it. They also look to see whether or not the patch created has done its job effectively. Among the skeptics were two researchers at Google, Tavis Ormady and Michal Zalewski. You remember, the guy who created AFL. Zalewski started Fuzz Testing Bash, identifying and isolating interesting syntax based on coverage signals. For the first few hours, AFL kept finding issues already known. And then he started to find new flaws in Bash. These were designated CVE 2014-6277 and CVE 2014-6278. Meanwhile, Ormady discovered that he could convince Bash parsers to keep looking for file names for output redirection beyond the boundary between the untrusted string and the actual body of the program that Bash was being asked to execute. In other words, he could piggyback malicious code. This was designated CVE 2014-7169. So that's 3 additional vulnerabilities on top of Shesla's initial finding, going much deeper into the problem. Then, Todd Sabin and Florian Weimar of Red Hat independently disclosed a static array overflow in the Bash parser. This was CVE 2014-7186, which is the 5th Shellshock vulnerability. While Weimar went off to find a one-off counter error in Bash, that became CVE 2014-7187. So there are now 6 vulnerabilities associated with Shellshock, and all found mostly through fuzzing within a 2-week window. Chet Ramey, meanwhile, was producing updated versions of Bash that incorporated all these new findings. By the beginning of October 2014, 3 weeks after Shesla first reported his finding, Zalewski completed his fuzzing of the latest patches and announced that Bash was indeed hardened and would prevent Shellshock from working on a patch system. In a blog, he summed up that the shell function import feature in Bash was clearly added with no basic consideration for the possibility of ever seeing untrusted data in the value of an environmental variable. This lack of a threat model seems to be a core issue. Not to put a fine point on it, but damn, that's an accurate accounting of Shellshock. Wait, so that's it? I said at the beginning that Shellshock was perhaps the most dangerous vulnerability ever reported. It's a 10, and it was ridiculously easy to exploit. So where's the worm? Where's all the carnage? In the beginning, there were some reports of exploits in the wild, but not much. Wired reported some botnets were using the initial Shellshock vulnerability to spread, but later patches mitigated that. And then, more importantly, there was a massive Yahoo data breach that was reported only a few weeks after Shellshock went public. But Yahoo quickly confirmed that the breach, the largest in US history with over 3 billion, that's billion with a B, user accounts affected, was not at all related to Shellshock. The thing is, security is a tricky thing. As Futurama reminds us, sometimes when you do the right thing, it seems as though you've done nothing at all. So rather than ask, why didn't it break or crash or produce a worm, we should instead talk about what went right. Although the initial vulnerability was misunderstood, as more and more researchers looked at Bash, they began to fuzz test it more. They started to expose the underlying issue. There was communication, and more importantly, there was cooperation and coordination. Remember, given enough eyeballs, all bugs are shallow. It seems like fuzz testing comes in fits and spurts. I mean, in 1995, Miller published 4 academic papers calling for more fuzz testing. Then in 2014, the Linux Foundation embarked on a process to secure open source software. It seems that at times not much happened after that. Actually, that's not true. In April 2012, Google announced ClusterFuzz, a cloud-based fuzzing infrastructure that is used for testing security-critical components of the Chromium web browser. In September 2016, Microsoft announced Project Springfield, a cloud-based fuzz testing service for finding security-critical bugs in software. And in December 2016, Google announced OSS Fuzz, which allows for continuous fuzzing of several security-critical open-source projects. Maybe the fact that we haven't had recent examples of cleverly named vulnerabilities with cute logos is not to say that we're not testing enough. Maybe it's to say that the process is finally starting to work. There may not be many more juicy vulnerabilities in Bash or OpenSSL, or in old code still in use, but we're producing over 111 billion lines of new code every year. And if we manage to stay on top of all that, shifting left with our testing, integrating fuzz testing into our CI/CD, then hopefully we won't ever see another Heartbleed or Shellshock again. Stay up to date with the Hacker Mind by following us on Twitter at the Hacker Mind in LeetSpeak. Hey, before you go, remember to subscribe to the Hacker Mind and never miss another episode. You can find us on Google, Apple, Amazon, Spotify, so many different platforms. Check us out. This podcast has been brought to you commercial-free by For All Secure. For the Hacker Mind, I remain your continuously fuzz testing Robert Vamosi.